In this video, we will discuss the dining philosopher's problem and will implement the solution using threading. So, the problem statement is 5 silent philosophers sit at a round table with bowls of spaghetti. Forks are placed between each pair of adjacent philosophers. So, there are 5 philosophers 1, 2, 3, 4, and 5, and we have 5 sets of forks placed next to each other. Each philosopher must alternatively think and eat. However, a philosopher can only eat spaghetti when they have both left and right forks. So, a philosopher can only eat when they both have the left fork and then right fork. Each fork can be held by only one philosopher, and so a philosopher can use the fork only if it is not being used by another philosopher. After an individual philosopher finishes eating, they need to put down both forks so that the forks become available to others. A philosopher can take the fork on their right or the one on their left as they become available, but cannot start eating before getting both forks. Eating is not limited by the remaining amount of spaghetti or stomach space. An infinite supply and an infinite demand are assumed. Design a discipline of behavior such that no philosopher will starve, that is, each can forever continue to alternate between eating and thinking, assuming that no philosopher can know when others may want to eat or think. So the solution or implementation which we can do, or the pseudocode which we can write for solving this problem is that, let's say philosopher 1 first pick up the left fork and then pick up the right fork and eat, and then put down the right fork and then put down the left fork. So in this case, when philosopher 1 is eating, philosopher 4 is also eating because the left fork of the philosopher and the right fork both are available. So 1 and 4 will be eating at the time when philosopher 1 is eating along with philosopher 4, because left and right forks are available. Now, philosopher 1 will put down the right fork first and the left fork. Now, philosopher 2 has both the forks available, so philosopher 2 will start eating, and at the same time, philosopher 4 will put down the right fork and put down the left fork. So now, philosopher 5 has both the forks available, so philosopher 5 will start eating. When philosopher 2 stops eating, then he will put down the right fork first and then left fork afterwards. Now philosopher 3 has both the forks available, so he can start eating. So this is how we will implement this solution. So we'll be implementing following pseudocode using lock and synchronize. While true, think, pick up left fork, pick up right fork, eat, put down right fork, and then put down left fork. Now let's implement the solution in IntelliJ. First, we will implement a simple solution using locks. So in this case, we will create 5 locks for each fork, and afterwards we'll be using the left fork first, lock the left fork and then lock the right fork. And we will implement the left and right fork locks for all the philosophers. So let's implement the solution. First of all, let's create a new package, and then the package name is com.javathreading.example. And inside the example, we'll create a new Java class, and the class name is dining philosopher. Let's create public static void main PSVM, and the first thing what we'll do is that we will create locks, and we'll be using forks as locks. So there are 5 forks, so we'll be creating 5 locks. Static lock and fork 1. So fork 1 is equal to new re-entrant lock, and static lock fork 2 is equal to new re-entrant lock, and static lock fork 3 is equal to new re-entrant lock. Now static lock fork 4 is equal to new re-entrant, and static lock fork 5 is equal to new re-entrant lock. So we are using forks as locks. Now let's create threads for each philosopher. So let's do new and then thread, and using lambda expression, or start. And here the first thing what we'll do is that at this point philosopher 1 is thinking, so let's print out philosopher 1, complaining about the spelling, philosopher 1 is thinking. Now philosopher 1 will pick up the fork on the left side first. So spoon. So philosopher 1 has the fork 2 on his left side. So first we'll get the lock on the fork 2. Now we'll print out philosopher 1 picked up left fork. Now he will pick up, or will look to pick up, the fork on his right side, which is the fork 1. So he need to get a lock on the fork 1. Now we'll print out. Once he get the lock, then it means that he picked up the fork on the right side. So now he is eating. So philosopher 1 is now eating. And when he finished eating, then he will put the fork 1 first, dot unlock, and afterwards he will do fork 2 dot unlock. We'll be repeating the similar things for all the philosophers. So let's go through this code again. So first of all, philosopher 1 on his left side is the fork 2, on his right side is the fork 1. So when first of all philosopher 1 is thinking, when he picked up the left fork, then philosopher 1 picked up the left fork, and then afterward he's waiting for picking up the fork 1, which is on his right side, and then once he picked up the fork 1, then he is eating, and then after eating he will put down the fork 1 first, which is the right fork, and then we'll put down the left fork afterwards. So fork 2, fork 1, and then fork 1 release, and then fork 2 release. Now let's copy this and then paste it for the philosopher 2. So here philosopher 2, and then philosopher 2, and then philosopher 2 on his left side is fork 3, and on his right side is fork 2. Now for the philosopher 3. Philosopher 3 has fork 4 on his left side and fork 3 on his right side. So for philosopher 3, first on his left side is fork 4, and then on the right side he is fork 3, and then he's putting back the fork 3 and then putting back the fork 4. Now let's copy this. For the philosopher 4, philosopher 4 on his left side is the fork 5, on his right side is the fork 4, and he's putting back fork 4 first and then fork 5 afterwards. And then philosopher 5 has fork 1 on his left side and fork 5 on his right side, and similarly he's putting back fork 5 and fork 1 in this order. This is so that's all for the implementation. Now let's run this program. So you can see that philosopher 2 is thinking, philosopher 1 is also thinking at the same time. Philosopher 2 picked up left fork, philosopher 2 is now eating, philosopher 1 picked up left fork, philosopher 1 is now eating, philosopher 3 is thinking. So if you look at the eating messages, 1, 2, 3, 4, and 5. All the philosophers has eaten the spaghetti. So this is the simple pseudocode implementation which we have done with logs. In the next section, we'll be implementing a more elegant solution of this problem using synchronize, and we'll be going in a loop for this so that philosophers will continue eating in a loop.